For these examples, we're going to play with some more of the trigonometric identities, and we're going to do that by factoring. And a hint that you're going to factor, and this is not always true, but just a hint that you're going to factor is sometimes when you see a quadratic factor, you look at this and you say, okay, something's quadratic, then I can factor it. So just looking at an expression, if it looks like a polynomial expression that's quadratic, then that's a hint that we're going to factor. Now, what I'm going to do in all of these is remind you of what they could look like in algebraic form, and then we're going to convert it from algebraic form into trigonometric form. Let's take a look at the first example, which is 1 minus cosine squared x. Now, instead of thinking about this as being 1 minus cosine squared x, when we go to factor it, let me use a different color pen for this. Let's think about it like this. Let's think about it like 1 minus something squared, 1 minus a squared. Now, hopefully that looks familiar to you, and hopefully you also remember that that's the same thing as saying this is the difference of two squares. That's the same thing as saying 1 minus a times 1 plus a. And the structure of it's going to look exactly the same, except instead of having an a over here, we're going to substitute in for that a cosine of x. So 1 minus cosine squared x is the difference of two squares. And when we go to factor it, that's the same thing as saying 1 minus cosine of x times 1 plus cosine of x. And you can always distribute to check. 1 times 1 is 1. 1 times cosine x is 1 plus 1 cosine x. A negative cosine x times 1 is minus 1 cosine x, so those middle two terms are going to cancel. And then negative cosine x times positive cosine x, well, negative times a positive is a negative. And cosine x times cosine x is cosine squared x. So that works. Let's take a look at part B. Again, what I encourage you to do is I encourage you to think about what this would look like in quadratic form. We have something squared plus 2 times that same thing plus 1. And in quadratic form, something squared plus 2 times that same thing plus 1. This is what it looks like. And except for x, when we go to write it in its factored form, we're going to call that x tangent of a. Now think about how we would factor this. X squared plus 2x plus 1. Two numbers that multiply out to 1 and sum up to 2 are going to be 1 and 1. So this is the same thing as saying x plus 1 times x plus 1, which is the same thing as saying x plus 1 squared. Now again, remember that x is taking on that value of tangent. So when we go to factor it, we're going to have tangent of a plus 1 times tangent of a plus 1. And again, tangent a times tangent a is tangent a squared. Tangent a times 1 is plus 1 tangent a. 1 times tangent a is another tangent a, so we have 2 of them, and then 1 times 1 gives you 1 for that last factor. But instead of calling it tangent a plus 1 times tangent a plus 1, another way we could call it is tangent a plus 1 quantity squared. So this form, tangent a plus 1 quantity squared, is equivalent to saying tangent squared a plus 2 tangent a plus 1. It's in its factored form. It can't be simplified any further. Same thing up here. This can't be simplified any further. All right, well, let's take a look at this next example, where we have secant squared theta plus 3 tangent theta plus 1. In regards to simplifying this, I'm hoping that you can tell that this is going to be a little bit different from the examples before. And the reason is that the variables are different. This would be something like saying y squared plus 3x plus 1. So in regards to factoring it, we can't yet factor it. But what we can do is a little sneaky trick. Now, remember that we have an identity that compares secants and tangents, and that comes from the third Pythagorean identity. The third Pythagorean identity says the following. It says tangent squared theta plus 1 equals secant squared theta. So what that will allow us to do, if you take a look over here, you see the secant squared theta? That will allow us to rewrite secant squared theta in terms of tangent. We know every time we see secant squared, we can replace in for it tangent squared theta plus 1. So let's do that. We can call this tangent squared theta plus 1. And then just bringing this part over, plus 3 tangent theta plus 1. Well, let's do some tricks here. Let's combine like terms. We have a 1 and a 1. So this is the same thing as saying tangent squared theta plus 3 tangent theta plus 2. Now it's in that nice quadratic form. We could think about this in terms of being x squared plus 3x plus 2. right? And factoring x squared plus 3x plus 2 is the same thing as saying x plus 2 times x plus 1. Two numbers that multiply out to 2 and sum up to 3 are going to be 2 and 1. So when we go to factor this, instead of calling it x, we're just going to substitute in for it tangent of theta. So this is equivalent to saying tangent theta plus 2 times tangent theta plus 1. And again, the hint is here, anytime you have a mixture of two variables in these and we're asking you to factor them, see if you can use one of the Pythagorean identities to help you get it in quadratic form, or at least to get it all in terms of one variable. Tangent theta times tangent theta gives us tangent squared theta. Tangent theta times 1 is plus 1 tangent theta, plus 2 tangent theta is 3 tangent theta. 2 times 1 is 2, so it's equivalent to that form. It's pretty neat, huh? Okay, let's take a look at, and this, again, this is the answer simplified completely, and there's nothing else we can do with that. Let's take a look at part D. Now, in part D, in regards to factoring, normally or typically we first ask ourselves, does this have a GCF? And we kind of ignored it in the examples above because it didn't, but hopefully you can see here that in this case we do have a greatest common factor. And we're going to start up by factoring out sine squared of x from each one of these terms. Now when we do that, factor out a sine squared from sine squared secant squared, and we're left with secant squared. Factor out a sine squared from sine squared, and we're left with 1. So we can call this sine squared x times secant squared x minus 1. Now let's talk about secant squared x minus 1. In regards to secant squared x minus 1, that should sound a little bit familiar because not only now can we factor it, but now we're going to talk about simplifying or reducing it a little bit. And again, there's a ton of different answers. This answer is perfectly acceptable. I just want you to know some tricks for when we get to proving. So this would work, but we can reduce this or we can simplify this a little bit further. From the same Pythagorean identity that we talked about in part C, secant squared should look a little familiar. So we do know the following. We know tangent squared theta plus 1 equals secant squared theta. But what does this tell us about secant squared value minus 1? Well, look at this. If we were to subtract 1 from both sides of this equation, that tells us the tangent squared of theta is equal to secant squared theta minus 1. So anytime we see secant squared of a value minus 1, secant squared of some angle minus 1, that's equivalent to reducing it down to tangent squared. So we can rewrite this like this. We can simplify it a little further. And then we can continue along this vein or along this process, because in the examples before, remember we talked about how if we have something in terms of, or if we're simplifying a trigonometric expression, if we write everything in terms of sines or cosines, that will give us a little hint or help us simplify it a little bit further. And again, this answer is perfectly fine. Or another equivalent way of writing that, remember the tangent is the same thing as saying sine squared over cosine squared. And we can call this over 1. So another equivalent way of writing this is sine squared times sine squared is sine to the 4th x divided by cosine squared x. So this is an okay equivalent form as well.